In a previous seminar, I explained some of the logical successes of physics. Today I'm going to talk about one of the most fundamental failures in logic in physics, and that is the notion of time travel, specifically time travel in reverse. So I'm going to explain to you today why time travel into the past is impossible. The first thing I'll talk about are some of the logical paradoxes that seem to result from time travel into the past. Second, what is the physicist and the scientist response to those? And third, I'm going to explain with a new logical argument that you've never seen before why the physicists are wrong. We'll start with what is the proposal for time travel into the past? Well, time travel into the future is very easy, right? We're doing that right now. And in fact, using special relativity, if you go very fast, close to the speed of light relative to something else and then return to it, then you can actually have a different age than the people that you're returning to. So if you were to go very near the speed of light relative to the people on Earth for a certain amount of time, turn around, reverse, come back. When you come back, you will actually be younger than the people on Earth. That's not actually a paradox. It's very interesting. It's called the twin paradox. It's not really a paradox, but it certainly is a very interesting aspect of relativity that addresses how quickly we can move into the future. But there's no question that we can certainly move into the future because I'm doing it right now, right? We're all doing it right now. The question is, can you time travel into the past? That's what we're going to take a look at today. So what is the proposal that time travel in reverse into the past is possible? Well, there's this notion in general relativity of closed timelike curves. That is basically the physicists' explanation for how this sort of thing is possible. And you'd have to use wormholes. You've probably heard of this notion. Using wormholes and exploding them really big and then going through them, and then somehow that makes the distance to other places in space-time shorter than they otherwise would be. And so as long as you go really fast in them, you can get to an earlier place in time. This is all very speculative, but the point is that a lot of very smart physicists have claimed with absolute certainty that this is possible, that it is consistent with general relativity. For example, Stephen Hawking said that quantum theory, and I quote, should allow time travel on a macroscopic scale, which people could use. Wow. Kip Thorne, who won the Nobel Prize in Physics a couple years ago, said that general relativity predicts that time travel into the past is possible because there are, and I quote, no unresolvable paradoxes in time travel. Well, I'm going to show you why these notions are just silly and why these physicists are in fact incorrect using a logical argument that has never been shown before. Woofie, are you ready? You ready? Yes, we're going to do it. I'm going to explain it to you. Okay, so the first thing I want to talk about is this thing called the grandfather paradox. Now, another name for this is the matricide or patricide paradox, meaning killing your mother or father. So the idea is this: if you kill one of your parents or change something about the past significantly, then you couldn't exist to then go back in time. So that causes a time paradox. So we all recognize this. We all know this, and the physicists realize that, certainly this would not be possible. So what if instead we just say, all right, we're not going to go back and kill one of our ancestors. In fact, we're going to try to do as little as possible. Well, the problem is that events are chaotic. You've heard of the butterfly effect. I think it's something like the flapping of a butterfly's wings in Thailand or across the world could affect the weather here tomorrow. And the idea is that chaos, it results in nonlinear amplifications or changes to the physical world. And what that means is that small things can cause huge effects later. So because of the butterfly effect or chaos, even the idea of going back in time and just kind of, not doing much, just making a few changes, when you walk around, certainly the air that you're breathing would be changing the past. And as you're walking around, you're making footsteps that change the past, but you're trying not to change the past that much. Well, it doesn't really matter because those chaotic amplifications of those events could result in a future in which you're either dead or you decide not to time travel, or you're incapable of time traveling into the past. So again, the physicists recognize this. So what if instead you build a time travel machine that allows you to go back in time and do absolutely nothing except observe. Maybe you are cloaked in some invisibility blanket, like in Harry Potter. In the real world, you would have to have little eye holes for that cloak in order for it to provide you any benefit, because you need to be able to get the photons. Photons are pieces of light. So you need those light rays to actually come and hit your retina in your eyes to be able to allow you to see anything. So presumably you'd want to go back in time to at least experience something, right? To observe something. Maybe not even to smell anything or to hear anything, but at the very least to see something. Well, that requires light rays or light waves or photons to actually enter your eye and to register with them and to then be perceived by you as the events in the past. Now, the problem with that, remember, we're talking about not even going back and killing your grandfather to prevent you from existing, but simply going back in time and doing the bare minimum, just sort of like, being behind an invisibility cloak so that no one can see you, but at the very least you have little eye holes so that you can see what's going on. Here's the problem with that. Imagine, here's your eye, and that's the only thing that can accept any information from the past. And what you're doing is you're looking at a really beautiful flower in the past. So you've time traveled into the past, you're looking at a really pretty flower. And behind you is some bird. Now, as you're looking at the flower, you are still affecting the past at least to the extent that photons of light bounce off the flower and go into your eye so that it can register, so that you can actually see the flower, which is the thing that you wanted to do in going into the past. Now here's the problem. Right behind your eye was a bird that now in the past would have received that photon, but now doesn't receive that photon, right? Because your eye absorbed it. It doesn't just go through your eye, it has to be absorbed into your eye. So now it does not hit that bird. Well, quantum events can be, and often are, amplified. I call them highly amplified quantum events. But in general, we know that randomness in the world is ultimately caused by amplification of quantum events. So let's just say that it happened to be the case that this bird was using light information to figure out where to go. And in the past, if you hadn't traveled to the past, it would have received that light ray, and as a result of that, it causes the bird to go in some direction. Let's say that bird in the past would have gone in, or did go in this direction, right? But now, as a result of not receiving that light ray, it just happens to be one of those cases that hinged on a very small amount of information in the past, maybe a single photon or a few photons or some, relatively small amount of information. Now, as a result of not receiving that photon, what happens is the bird decides instead to just go in a slightly different direction. And that difference could be really, really, really tiny. But by the time, because of amplification, because of chaos, because of the butterfly effect, or in this case, the bird effect, that bird ends up in a far different place than it would have been had you not been in the past. So let's just say that, okay, so this particular case causes the bird to end up right here. If you hadn't time traveled into the past, it ends up doing something like this, and in the future ends up right here. It just so happens that at that point in the time in the future, you were right here. If you hadn't traveled into the past, then at some point in the future, you'd be here, but the bird would be way over here. You wouldn't see it. But because you did travel into the past, then now there's a slight change and an amplification, chaotic amplification of that event, which is the lack of receipt of a photon that it would have received otherwise, results in the bird being near you at that particular time in the future. But now let's just say that you're sitting here contemplating going into the past. You've built this time machine, let's say, and you're sitting here thinking, should I actually do it? It seems kind of crazy. Should I actually go into the past? And you look up into the sky, and it's very pretty. You're maybe looking at a sunset or something, and all of a sudden you see a bird fly by. And at that moment you say, life is good. I don't need to do anything. I want to be present in the moment. I'm going to be happy in the moment. I'm not going to try to seek out happiness by going to the past. I'm just going to enjoy the moment. So at that moment, you decide not to go into the past, whereas before, you would have been sitting right there but the bird was over here, and it wasn't enough to make you excited enough about the present to prevent you from going into the past. So if the bird had been here, you would go into the past. But by going into the past, you cause it so that the bird now ends up here, which makes it so that you don't go into the past. This is the exact same situation as the grandfather paradox, although instead of here, we have something drastic. You go into the past to kill an ancestor, which means you can't exist to go into the past. Here I've created a much more subtle example, where merely by going into the past and simply looking at something, even briefly, I've given you an example where that change to the past, the absorption of photons here, or the absorption of even a single photon here, could actually, through chaotic amplification of that quantum event, result in a future in which you don't go into the past, whether because you're dead, or you decide not to, or you never actually come up with the idea of time travel, and so forth. So in other words, this is another example of the grandfather paradox that presents itself even with the smallest possible change that you could make to the past. Got it, Woofie? Does that make sense? All right, good. Why is your tongue sticking out? The physicists know this. Most of them. Sort of. So for the ones who actually understand this scenario, and not all of them do, what is the response? The response is, and I believe this is Hawking's response, don't change anything in the past at all. As long as you don't change the information structure of the universe in the past at all, then time travel into the past is at least possible, is consistent with general relativity. From the example I've given, you don't even have to fundamentally understand physics to see what the problem is. In order to change absolutely nothing, keeping in mind that your mere presence there by observing anything or hearing anything already influences the matter and photons and state of the universe in the past. Knowing that, how do you go into the past and make it so that you don't change anything about the information structure of the universe at that time? Well, it means you can't even look. You can't see anything. You can't hear anything. You can't interact with the environment in any possible way, which means you can't get any information about the past, which means what the hell is the point of going into the past? In other words, it's sort of like, maybe I'll sell you entrance into the time machine that I've built that's going to take you back wherever you want to. Take you back 1,000,000 years or 1,000 years, whatever. But the only caveat is you can't get any information about it. You can't look out of it. You can't hear from it. You can't get any information from inside the time machine, but you're still going into the past. And then once you come out of it, I'm going to charge you the time travel fee because I sent you to the past. You just didn't get any information, right? I think you'd be pretty annoyed if that were the case, because the whole point of going into the past is to at least observe something. But the mere state, the mere situation of observing something necessarily causes changes to the past, and that's a problem. Now, the physicists, again, for the most part, know this. So they say you can't make any changes to the past at all. But I'm going to point out that even that is wrong, that even that is a fallacy, and this is an argument and a proof that you've never seen before. I'm going to explain Hawking and Thorne and all the others who talk about the possibility of traveling into the past are wrong. Okay, the reason that these physicists' response is incorrect is because the response is based on and depends on an unstated hidden assumption. And that assumption is that if we make small changes to the past, then we make small changes to the future. Big changes to the past, big changes to the future. So the assumption is that the magnitude of changes to the present would be commensurate with the magnitude of changes to the past. And I'm going to write this. If you don't like math, that's perfectly fine. Just ignore what I'm going to write. I'm just going to write this as the following. What this means, so T2, say, is the present, and then T0 is where you want to travel to. Now, I could just use T1 here, but you'll see later in the example. It just makes it clearer why I'm using T2 here. So the idea is that T0 comes before T2. That's what this means. T0 is less than T2. And so this right here, this portion right here, means the change to the state of the universe at time 0 caused by a time traveler traveling from time T2. That's what this change is. And this is the change to the state of the universe where the time traveler starts from at T2. So what this says is, so basically imagine this piece right here as being how much the time traveler changes the past, or changes the universe in the past. And this is how much the current state of the universe is changed. So what this says is, as the change that the time traveler makes to the past, as it approaches zero, then the change to the state of the universe in the present day should also go to zero. That's what this limit means. Again, if you don't like the math, it simply means that the less the time traveler changes the past, the less his future or his present, where he travels from, the less that future is affected. This is the underlying assumption of any idea, theory, hypothesis that posits the ability to travel back in time. This has to be true for Hawking and for anyone else who believes that travel into the past is possible. It has to be the case, as those changes to the past shrink to zero, that the corresponding changes to the future also have to shrink to zero. This is an underlying assumption of every one of those hypotheses. This is false, and I'm going to show you why it's false. Anytime you make a logical argument, you have to give all of your assumptions. I'm going to tell you up front that one of my assumptions is that we observe outcomes to quantum events. Now, this is a very, very, very believable assumption. As far as I know, nearly every physicist would or should agree with that assumption, because it doesn't matter whether you subscribe to the multi-worlds interpretation of quantum mechanics or Copenhagen or the many other varieties and flavors or interpretations of quantum mechanics. It doesn't actually make any difference, because if there's collapse, objective collapse, maybe it's caused by a GRW type collapse, maybe it's caused by consciousness, maybe it's caused by decoherence. If there actually is a collapse of a wave state, then of course we would observe the outcome of that wave state. But if there isn't a collapse, such as in many minds or the many worlds interpretation of quantum mechanics, it doesn't change the fact that we still observe results or outcomes of those quantum measurements, but they would just simply claim that it would split into different universes or branches in which all of those different outcomes obtain. But it doesn't change that in any given universe, those observers observe a particular outcome. In the last seminar, I taught you a little about the basics of quantum mechanics, the easy stuff, the fundamental stuff, the fact that quantum mechanics is simply about the fact that the universe does not contain infinite information, and therefore nothing can be specified or measured with infinite precision. So quantum mechanics is simply about what happens when events in the universe could depend on, or do depend on, the fuzziness in that imprecision. And I gave you an example in the last seminar. Let's just say that, and this is the reason I said time 0 and time 2. So let's just say that there is some observer, Alice. At time t0, she has placed an object in a superposition state of two mutually exclusive states. So just a simple binary superposition. So the state of object O, and we write this in bracket notation, is just simply some complex coefficient times state x, where state x corresponds to one of those two possible measurement outcomes, plus some complex constant y times state y, where y is the other of those two possibilities. X and y tell us what the likelihood of measuring each of those possible outcomes is. So if you don't like how this looks, the symbols, it simply says that at time t0, Alice knows that object is in a quantum superposition, where if she measures it, she's either going to find it in state x or y. Maybe those are positions x and y. So that's it. Now, at time t1, the object is measured, and it is found that O is in state x, or even just O is located at x. And then at time t2, she wants to travel back in time to time t0. And I'm going to show you the problem with this, So Alice travels to T0 with the intention of making no change to the universe whatsoever. Why? Because we already saw before that making any change to the universe at all could be problematic because of chaotic amplifications. So we want to be able to go back in time and make no changes whatsoever, which is exactly what physicists say is necessary to travel back in time, even though that'd be silly because then you can't get information about what happened in the past, so it defeats the point of traveling in time anyway. But my point here is to show why this is logically impossible from the get-go. So she goes back to T0. There are only two possibilities. And by the way, I just want to reiterate that again here, when O is found to be in state X, that does not conflict with any interpretation of quantum mechanics because we all agree that, in this case, Alice lives in a universe at T1 in which O is in state X, or O is found at location X, or whatever the state happens to be. So at time T2, she travels back to T0. What are the implications of that? Well, the first implication is that only the following are possible. We'll say, A, it is certain that O will be found at X. If there's only two possibilities, A and B, well, it's the negation of this. It is not certain that O will be found at X. Those are the only two possibilities, right? Logically. Well, here's a problem. A, if it is certain that the object will be found at X, remember this is at time T0 when she goes back in time. At that time, she travels to T0. At that time, if it is the case that it is certain that O will be found at X, what that implies is that O was not in a superposition over states X and Y. I'll say that again. If there's only two possibilities when she travels back to time to T0, X, either O will with certainty be detected at X, or it is not certain that it will be detected at X. The problem is, if it is certain that O will be found at X, what that means is that O was not in a superposition over states X and Y, which means that she has already changed the past, if A is true. So A can't be true. So let's see, what are the implications of B being true? If B is true, what follows from that? Either C or D, and I'll squeeze them in here, C or D. So if B is true, that it is not certain that O will be found at X, then either at T1, O is detected at Y, or O is detected at X. These are the only two possibilities if B is true, and we know that A can't be true. Well, the problem with C is this. If at T1 O is detected at Y, then she has changed the past. Because previously at T1, O was detected at X. O was detected to be in state X. So it cannot be C. So the only thing remaining is that if it's possible for Alice to travel to T0, for her to not make any changes to the past at all, D has to be true, which is that O is going to be detected at X at time T1. Okay, so I've rewritten all this to clean up the board here. So remember, at time T0, O was in a superposition over X and Y. We're left of those four possibilities when Alice travels back to that time. We're left only with D, which is that at time T1, O is detected as state X or at location X or whatever it happens to be. Now here's the problem with that. The likelihood of O being found in state X, according to this, is, and I'm going to try not to scare you off with math here, but it's called the Born rule, and it's simply the magnitude of that coefficient X squared. The reason we have to take the magnitude first is because it could be a complex number. So the probability of finding the object O in state X at a later time is just this value. So what this tells us right now is that in order for her to go back in time from time T2 to time T0 and be certain not to, well, not even be certain, and not to make any changes in the state of the universe, it has to be the case that she doesn't change this superposition, but she also does detect O in state X at time t1. The problem with that is that the likelihood of that happening by accident is this value. And the physicist might just say, oh, okay, it's, we don't know the size of this. Maybe this turns out to be 50%, maybe 10%, maybe 99%. But the point is there's still a possibility that she can go back in time and not make any changes to the universe. Once again, not getting any information about the universe because she can't change the universe, but nevertheless, it's still, in their eyes, possible to go back in time. Here's the problem. How many events happen between t0 and t2 in the universe? How many of those are quantum events? How many of those are random events? Well, it turns out quantum events are happening all the time at a very, very huge rate. Even when air molecules bounce off of each other, they will cause decoherence of their own quantum states. It happens very, very frequently. So let's just say that there was a second event that happened between t0 and t2. And let's say that those coefficients were W and Z, hypothetically. What's the likelihood then of both of those events resolving in exactly the way that Alice originally measured them? Well, it would be exactly the same. What you'd have to do is multiply it by the magnitude squared of one of those coefficients. And when you do this, when you multiply a number that's between 0 and 1, which is what a probability is, when you multiply them together, they get smaller, which is the reason that the likelihood of a whole bunch of independent events happening is the product of their probabilities, and it gets smaller and smaller. So now we have to multiply these together. Well, let's say that there are, in general, n quantum or random events between times t0 and t2. What does that imply? What it means is that this implies that the probability of all of those events resolving in a particular way, now each of those complex coefficients will be different, but you can see that there's going to be, one term, two terms, 3, 4, all the way up to n. And so what that ends up meaning is that the likelihood of all of them resolving in exactly the same way that Alice, in fact, measured them by the time she reaches t2 is on the order of some value to the 2n, which means this is actually an exponential decay, something like that. Well, this would be a different n than that. But the point is, for those of you who like math, understand math, as n gets large, an exponential decay goes really, really, really small and approaches 0. Okay, we're almost there. So then the physicist might say, okay, well, how do we know how many events there are, right? I mean, maybe it's not that many. Maybe n isn't that big. The problem with that is that time travel into the past, that notion, that belief, that hypothesis, depends on this assumption. But there were no constraints on these two times, t0 and t2. There's no constraints. It must be true. It must be true that if time travel into the past is possible, then you can go a second before now or a million years from now. Both of those depend on this assumption. So because the distance between these can be made arbitrarily large, n can be made arbitrarily large, this probability gets to 0. The likelihood of that happening by random chance approaches 0. So in order for Alice to go back in time from t2 to t0 and not affect the universe at all, not affect the state of the universe at all, it must be the case, there was only one remaining possibility of those 4 statements. It must be the case that at t1, object O is detected as state X. And that must also be true for every other quantum event that happens between times t0 and t2. And because of that, the likelihood of that happening by random chance goes to 0 as n becomes almost anything, because quantum events are happening so quickly in the universe. Every single one of those must resolve in the way that she actually measures or would measure at t2 before she went back in time to t0, or else this all falls apart. And because of all this, because this probability goes to 0, this is false. This assumption is false. And so the physicist's argument that going back in time is at least possible or consistent with the known laws of physics is absolutely false. And notice, by the way, what I've shown you has nothing to do with chaos. We already know that chaotic amplifications wreak havoc. I'm saying this is an example where she doesn't interact at all with the system, but yet it still essentially guarantees quantum mechanically that there will be changes to the universe. And again, this has nothing to do with what interpretation you take, because ultimately we all agree that Alice will be in a universe in which she makes these various quantum measurements and gets certain outcomes. Time traveling into the past is false. What do you think about that, baby? Time travel's false. She gets it.